Welcome back to The Explainer. Today, we're diving into a massive historical shift in how software engineers model data. We're looking at NoSQL and document databases. Let's get right into it. Okay, let's dive into this. If you've ever built a backend, you've probably felt this exact pain. We're going to frame this explainer around a reoccurring scenario I like to call the tale of two architectures. Imagine you and I are building a rapidly evolving restaurant booking platform. At first, everything is super simple. But what happens when our data, things like varied menus, opening hours, and nested user reviews, simply refuses to fit neatly into the rigid, flat rows and columns of a traditional relational database? To really understand this wall we hit, we've got to look at a concept known as the impedance mismatch. You see, most modern application development is done in object-oriented programming languages. We build our code using these rich, nested data structures, objects within objects, lists, arrays, the whole shebang. But for a very long time, the default was to take that rich data and force it into relational SQL tables, which are strictly flat. Translating our modern application objects into these flat tables feels quite literally like taking a perfectly good car apart every single time you want to park it in your garage, and then having to reassemble all the pieces every time you want to take it out for a spin. It creates just a ton of friction. Just think about a standard professional profile, like what you'd see on a networking site. To fit this into a relational database, the data has to go through a technique called shredding. The user's basic info goes into one table, their jobs into another, and education into a third. If we map this back to our restaurant booking app, it's the exact same nightmare. We'd have to split a single restaurant's basic info, its opening hours, its photo URLs, and its menu items across multiple different tables. So just to load one single restaurant page for a hungry user, the database has to execute messy, multi-way joins to stitch all those shredded pieces back together. So, the crucial point here is that engineers wanted a better way. They wanted to park the whole car at once and enter the document database. This is a massively popular type of NoSQL data store that essentially tells developers, hey, keep your objects whole. Instead of shredding data into relational rows and columns, a document database stores self-contained nested data structures, typically as JSON documents. So if our restaurant has a list of operating hours or an array of tags, we don't need separate tables. We just embed them directly inside the restaurant's single document. Notice how this one-to-many relationship naturally forms a really clean tree structure. Whether it's a user and their previous jobs, or a restaurant and its nested list of menu items, the parent record sits right there at the root. All the nested details branch out directly beneath it. In a document database, this entire tree structure is preserved on the disk exactly as it is. It maps perfectly to the JSON objects you're probably already passing around in your backend code. It's just a really natural fit. This brings us to our everyday engineering choices, particularly around schemas. Relational modeling uses strict schema on write. Basically, the database acts like a bouncer. If your data doesn't perfectly match the upfront table structure, it gets rejected right at the door. Document modeling, however, uses flexible schema on read. It's totally up to your application code to interpret the JSON document when you read it back. Agile teams absolutely love this, because it means they don't have to run massive, terrifying database migration scripts just to add a simple new feature. If you've ever held your breath while a migration runs on a production database, you know exactly why this is so appealing. Aside from that flexibility, there's another massive benefit here, and it's all about performance. We call it data locality. Because our entire restaurant profile, its address, its menus, its photos, is stored as a continuous string in a single document, everything is just in one place. The database engine doesn't have to go hunting all across the hard drive to assemble rows from 5 different tables. When you need the restaurant data, bam, it's all right there waiting for you. We can trace the advantage of this locality by looking at a concept called denormalization. Denormalization essentially means storing related data together to speed things up. Look at how simple the data retrieval flow becomes in a document database. Step 1, your application queries the restaurant ID. Step 2, the database fetches the entire JSON document from the disk in one continuous read. Step 3, your application renders the web page immediately. By completely bypassing the need to join multiple tables together, read operations for these self-contained documents become incredibly fast and efficient. It's a real game changer for read-heavy apps. But of course, there's no such thing as a perfect architecture, right? As our platform grows, we inevitably hit new roadblocks. It's a foundational truth in system design that as you add features to an application, your data inherently becomes more tangled and interconnected. At first, our restaurant pages were totally self-contained. But pretty soon, users start making reservations across multiple tables. They start leaving reviews that link back to their social profiles and specific dishes. Suddenly, our isolated documents are under some serious strain. And this brings us to the trade-off reality check. That clean, beautiful tree structure we loved earlier, it starts to fail when we begin dealing with many-to-one and many-to-many relationships. For example, what if 1,000 users want to reference a single standardized cuisine tag, like Italian? Or what if a single review needs to reference both a specific user and a specific restaurant? In a relational database, you just use an ID and join the tables together. Easy. But here's the catch. Document databases often have very weak, or sometimes completely non-existent, support for joins. The tree structure simply isn't built for a complex spider web of connections. So what actually happens when your database doesn't support joins? Well, you run into these specific architectural trade-offs introduced by NoSQL. To keep your reads fast without joins, you're forced to denormalize, which usually means you have to duplicate your data. If you have a standardized cuisine name, you might have to literally copy that exact string into every single restaurant document. But this extensive data duplication leads to complex multi-document updates, and because the database lacks that built-in join support, it shifts a massive burden right onto your application code. Your app now has to do all the heavy lifting to keep that duplicated data consistent. Let me ask you a provocative engineering question to make this practically real for a second. Imagine in our app, a user decides to update their profile photo. But to make loading fast, we previously denormalized that photo URL by copying it directly into 50 different restaurant reviews they've written over the years. What happens now? Well, your application code has to go find all 50 of those reviews and update them one by one. If your server crashes on update number 25, you now have an update anomaly. Half the platform shows the old photo, half shows the new one. This is exactly the kind of consistency nightmare that relational SQL databases were originally invented to solve. To summarize these two distinct design philosophies side by side, relational SQL wins handily when your data is highly interconnected and requires complex joins. It relies on explicit schemas, and updates are simple because data is centralized. You update that profile photo in exactly one place and you're done. On the flip side, document NoSQL shines for self-contained, tree-like data. It offers incredible schema flexibility, and read performance is phenomenal due to data locality. But the tax you pay for that is the complexity of updating heavily duplicated data. Which brings us to our final takeaway. As you navigate system design, remember this. NoSQL isn't fundamentally better than SQL, and SQL isn't better than NoSQL. They just represent completely different sets of compromises. Designing a great data system is never about finding a perfect silver bullet that magically solves everything. It's about looking really closely at your application's specific read patterns, its write patterns, and how its data relates, and then intentionally choosing the right trade-offs. So, my question to leave you with today is this. What compromises is your application willing to make today? Thanks so much for joining me for this explainer. I really hope this helps you architect better, smarter systems. Catch you next time.